RLE. Again, that E is the magnitude of my electric field. Why is red not an option here? We'll pretend that's red. All right. L cancels out, which is fortunate since we made that side up. So my electric field, the magnitude of my electric field is equal to the linear charge density divided by 2 pi r epsilon sub naught. And there we go. The electric field from an infinite line of charge with the uniform charge distribution.
From a infinite charge?
Infinite line of charge.
So to find lambda, we would have to have the enclosed charge and the length of the cylinder.
You would most likely be given lambda.
Okay.
In a closed cylinder.
It probably wouldn't help for me to say, give an infinite line of charge with a total charge of infinite.
Do you do with other shapes?
Besides a line, or besides the cylinder?
Cylinder.
You generally pick the shape to match the situation that you need. So for a line, the cylinder makes most sense. If I have a point, a sphere makes most sense. If I've got an infinite plane, a cylinder. Which brings me into the next one. Questions before we do the cylinder? Before we do the infinite plane of charge?
So that number, the electric field, is any point on the whole cylinder other than south, right?
If I'm a distance r away from the line, that will be the strength of the electric field.
Okay.
As r gets smaller, the magnitude gets bigger, which makes sense. All right, so now I have an infinite plane of charge. And I want to know what is the electric field, a distance r away. So what I'm going to do is I'm going to create a Gaussian surface again. This time my Gaussian surface, and on the other side too, is basically a cylinder. In other words, so imagine I've got a piece of paper here and I'm holding two cans together. I know that my total electric flux is equal to the enclosed charge divided by epsilon sub naught. So now we have infinite plane of charge with uniform surface charge density. So sigma is equal to charge divided by area.
What is that letter?
Sigma, lowercase sigma.
Okay.
It looks like an O with an extra flare to it,
So it's like an upside down U.
in some sense. The O is wearing a scarf and the wind is coming from its left.
Well,
That is going to be equal to the electric flux through the left cap plus the electric flux through the right cap plus the electric flux through the side. Well, again, by symmetry, I know my electric field is going to be going off to the right and to the left. So my electric flux through the side here, this time it's 0. Because my electric field is perpendicular to the area of the side. Because my side will be going basically, if that's my infinite sheet right there, my cans like this, the area vector would be anywhere, pointing anywhere like that, but my electric field is pointing back those ways. Through the left cap and the right cap, again, by symmetry, the electric field anywhere on this cap should be the same. And so let's make the area, the radius of this cylinder to be big R. So I end up with the electric field, magnitude of my electric field times pi big R squared. My area vectors in the same direction as the electric field on the right and on the left. They're still in the same direction. So those would be the same electric flux. My enclosed charge is going to be sigma times A over epsilon sub naught, where A is pi R squared. It's the area of this dotted circle right here. So I'm left with my electric field strength. Well, pi R squared cancels out, so I'm left with just sigma over 2 epsilon sub naught.
And we would be given sigma for those two.
Yes, or enough information to find it. Now, the reason why I say at this time, given enough information to find it, is that the question is, how can this assumption here, this infinite plane, can we make that assumption elsewhere? And yes, we can. If I consider this wall right here, it's obviously not infinitely large. But if I'm this close to it, it would pretty darn close, good approximation to say that it's infinitely large. Now, if I'm where Ethan is, no, probably not a good approximation. But if I'm really close to the surface, making the assumption that it's infinitely large is valid.
Almost an electron small. Get that small to it.
Yeah, you have a charge that, generally the rule of thumb is, if you think about the dimensions of it, that the distance is less than 10% of the smallest dimension. Therefore, not that one. That one. If I have an infinite plane of charge here, let's say positive Q. I know that I have an electric field that's moving away from it. And the magnitude of the electric field is sigma, whatever that surface charge density is, divided by 2 epsilon sub 0. And over here, sigma over 2 epsilon sub 0. Into it, I add another plate, this time with a charge of negative Q. It's a negative charge, so my electric field lines go towards it. So I have an electric field going towards it, and occasionally get that nice black on black look. And the charge of that is sigma over 2 epsilon sub naught. I'm assuming the two plates are the same size. I'm assuming the distance between them is small. And sigma over 2 epsilon sub naught. So if I'm over here, to the left of them, what is my total electric field?
Zero.
If I am over here, we can do that in some other stunning color. If I'm over here, what is my total electric field?
Zero.
If I'm in between, what is my total electric field? Not infinite, not zero. I have two electric fields going in the same direction. Each magnitude of each one is sigma over 2 epsilon sub naught.
So it'll be sigma over 2, sigma over.
At times 2.
Yeah, otherwise known as.
Sigma over 4. No, 4 sigma over 4 epsilon.
If I multiply this times 2,
Oh, you know what? So 2 sigma over
Sigma
epsilon.
over fake E, so over 2.
sigma over fake E epsilon. Fake E is 0. Epsilon. This is known as a parallel plate capacitor. If I have two plates that are charged opposite signs, same overall magnitude, just opposite signs, that are really close to each other, I have what's known as capacitor. And that is something that we will hit on in more detail in the end of chapter 19 and then chapter 20 and 21.
For the most part,
23.
I haven't looked, but for the most part, do we just follow the order of the chapters? Because I spoke to
Yeah.
this semester.
Yeah. There's one jump that I do and then I jump back, but what is it? I am going to derive the speed of light, which blends very naturally into relativity. And so I used to skip AC circuits and just go with that flow. I will touch on relativity, and then I'll jump back to AC circuits, and then we'll jump back and get into relativity. I hope all of you have a wonderful day.
Do we have a lab tomorrow to print out?
Yes, there is a lab. If it's not ready, when I get back to my office, I will make it ready. If it's not ready by noon, then assume I will bring it. But it should be ready by noon, unless I get distracted. So the R2 is indicating, with a hat, indicating that the second charge is for my reference. So if this ends up being negative, that means the force is on charge 1 is towards the second charge. If I ended up with a positive here, it means it's away from the second charge. Yeah, if it's negative, it's away, it's towards, if it's positive, it's away, and the 2 just tells you what you're towards or away from what.
All right, thank you.
You'll be in your office today for